And one algorithm for graph is shortest path, finding shortest path, and sequentially we are going to move towards the Dijkstra's shortest path algorithm. So this shortest path algorithm, what things we need is that if we have to find shortest path, we need to have some weights on the graphs, and we need to have edges and directions, so that how or from this particular node v3 we can go to v1 and this much time or miles, or so this might be some unit. So 4 might be 4 miles, 4 might be 4 minutes to reach, or 4 might be 4 hours to reach. So that weight needs to be there in order to find the shortest path in a given graph. So whenever we have such a graph and with some edges which have weight in them, then we will be given what is the path, or what is the source vertex and what is the destination vertex, and from which vertex to which vertex we want to traverse, and then there might be different possible paths. So here, let's say if I have to traverse from v3 to v5, there are different possible paths. I can go from v3 to v1, then I can go to v2, and I can go to v5. So the direction and weights are very important. Then another path might be I can go to v1 and then v4 and v5. So this is another path. So from v3 I can go to v1 and then v4 and then v5. Is there any another path that I can take? So I can go from v3 to v1 and v1 to v2. So v3 to v1. Now v1 to v4, v1 to v2, v4 and v5, v1 to v2, v4, v5. Now one way of doing it is finding all possible paths. Finding all possible paths and then calculating all possible paths and then finding the shortest path. But that is called as the brute force technique, where you just find all possibilities and then you pick the minimum one. But as you can see, in first you will require a lot of efforts to find all possible paths. Then you have to calculate all possible paths, and then you have to pick the smallest one. So this is not a very efficient way of doing things. So many people, many mathematicians, they came across different algorithms to find shortest path. Now if you remember something we discussed in other classes, is that finding the minimum spanning tree, and that is also having very similar approach of this, where in different ways we can start and then find the tree. But the difference between this and finding minimum spanning tree and shortest path algorithm is that in minimum spanning tree we have to cover all the vertices, and then the path which covers all the vertices but is also a minimum path. But in finding shortest path algorithm, there is no such restriction that we have to cover all the vertices. We can take any way or any path possible which might include 2 vertices or might include 6 vertices. So irrespective of how many vertices the path includes, that path has to be minimum possible path from given 2 vertices from source to destination. So this is the difference between minimum spanning tree and shortest path. In minimum spanning tree, we have to cover all the vertices. In shortest path, we don't. So here you can see if we pick the first path, v3, v1, v2, v5, we are not going to v6, v7 and v4, and that is absolutely fine. As long as we have a path, we can reach from source to destination in a minimum amount of weight. So here, as I said, weight might be time, or weight might be cost of reaching from one node to another node, and as long as we can reach in smallest or shortest path, we are good. So here in this particular weighted graph, again, as I said, it may represent distances, cost, and then when given two endpoints, we have to find a path. So here two endpoints given are Honolulu to Providence, and then as we can see, we can take various different paths to reach from one to another, and then this might be the possible way of going from one destination to another destination. So what are the properties of, I think we discussed this, so I will just go into discussing how we are going to find the unweighted shortest path. So if the weights are not given, then how we find the shortest path? We consider that all weights are 1, and so the path with minimum path length, or path having minimum vertices, will be the shortest path. So it is also possible that we have been given some path where we do not have weights, and then ideally we are going to consider all edges weigh 1 each, so that the shortest path will have the shortest or the minimum number of edges in it. So we cannot really take care of the negative costs here, because every time we are going to add, and so if there is some path having negative cost, then we don't know how we want to deal with that particular negative cost. So ideally, whenever we are tackling with shortest path problems, we are looking that all weights on the graph are given in positive. So let it be a very small positive number, but there is some cost associated to go from one endpoint to another endpoint, and that will be always be a positive number. So that is the assumption. Another thing is that these three properties. So whenever we are calculating shortest path, and we are let's say we have a shortest path which can take us from Honolulu to Providence, and then we are following this particular path from Honolulu to Orlando. Then in that case, this path Honolulu to Orlando, this is the shortest path which can take us from Honolulu to Orlando. So this is how we are going to assume, or these are the important properties. So we cannot have any path better than one take us from Honolulu to Orlando in a smaller distance than what we are getting in this path, because this is the shortest path. So the sub path of this shortest path is also the minimum possible, or is the shortest path which we can take us from this destination to this destination. So those are so this is the first property. So sub path is itself a shortest path, and then there is a tree of shortest path from start vertex to all other vertices. So if you follow the path, we are always going to get to a tree structure which takes us from the starting vertex to all the other vertex that we can reach. And then here is one example of the tree of shortest path from Providence to Honolulu. So here is one how we want to calculate. So let's say in this case the source S is V3. So V3 is our starting point. Okay, and now since we have not given any weights, we are going to consider that every time we go or we traverse any edge, it takes us 1 unit. So we can say that from V3, where can we go? So we can go to two places. Either we can go to V1 or we can go to V6. So in the next iteration, V1 is one distance away from V3 and V6 is also one distance away from V3. Now next, uh, find the vertices whose shortest path from S is 2. Now after we reach at V6, we cannot really go to any other vertex. Okay, so this is kind of, we can say, a dead end. We cannot go any further. But what happens at V1? When we come at V1, I have two options. From V1, I can either go to V2 or I can also go to V4. I can reach to V2 in 2 units. I can reach to V4 in 2 units, because 1 unit from V3 to V1 and second unit from V1 to V4. Again 1 unit from V3 to V1, second unit from V1 to V2. Now finally, when we come at V4 and V2, we are going to find what other places we can go to from either from V2 or from V4. So one next edge we have to find. From V2 we can come to V3, V5, so it takes 3 units. From V4 also we can come to V3 and we can come to V5. So here also it takes 3 units. Then from so here we can also go to V6 after V7, but let's stop here. So from V3 we can reach to V5 and then from V4 we can reach to V7. So both of this is possible with units 3, because it is possible to reach in these nodes in 3 edges. So that's how now if I have to find a smallest path between V3 and V5, I can say I can come to V1, then to V2, and then I can come to V5 in units. So this is the minimum possible distance that is needed to reach from V3 to V7 or V3 to V5. So this strategy for searching a graph is also known as breadth first search, because we start from one vertex V1, then we are really traversing breadth wise. So we are saying what are the all possible vertices I can reach from V1, which were V2, V4, sorry V3. From V3 we started, so with V1 and V6. So from V3 was the source node, we can go to V1 and V6. Now from V6 we cannot go to anywhere. Okay, so in the next level, which are the other nodes we can traverse from V1, we could go to V4 and V2. So V2 and V4 and so on. So every time if you see the traversal in the how we are traversing these vertices, then it is really in a breadth first search manner we are traversing this particular vertices, and then we are traversing layer by layer. So this level I can reach into 1 unit, this level I can reach into 2 units, then from V2 we can go to V5, and from V4 we can go to V7. So from V2 I can go to V5, from V4 I can go to V7, and to come to this level I need so in 3 units I can reach to these nodes. So this is similar to level ordering traversal of tree. Level by level we are doing that. Now if we understand this, now this is not really that we are not really using this technique, but this is to understand and to go to a very good algorithm, and this has been in use since last 30 years. It's called as the Dijkstra's algorithm for finding shortest path. So what we are doing here basically is that every time again we have been given some source vertex, and we have to find distance from this source vertex to any other v given, and then every time we start from vertex s and we keep on growing. So we first find how many vertices are there that I can reach from s, and then that is also called as growing a cloud of vertices, and every time I pick up the edge having the minimum distance in that particular cloud. So what are the different assumptions here is that the graph is connected. So you do not have some components like this and another component like this. So if you have graph like that, then I cannot really reach to this second disconnected component. And so I cannot find a path which goes from A to E in this case. So let's say these are the name of the vertices, and unless there is a way for me to reach to a C to D or B to D, I cannot reach from A to E. So the first assumption is that the graph is connected. Okay, and in this case the edges are undirected. So we are considering that it's not just a directed edges we are considering undirected edges. So if I can traverse from A to B, I can also traverse from B to A using the same distance. Third assumption is that edge weights are non-negative. So we do not want any negative edges because that will interfere with the capability of this Dijkstra's algorithm. So these are the assumption for us to use the Dijkstra algorithm. Now we grow a cloud of vertices, and every time eventually we will cover all the vertices to find the minimum possible shortest path. And again, like we did in the previous case, we are going to store dv as the distance of v from a particular source node s given to us. So every time for every vertex v, we are storing the possible distance from the source vertex, and every time we might update this distance. So as we find a better path to reach to v, we will update that distance. And at each step we are adding the cloud to the cloud the vertex u outside the cloud, and we will see that how the cloud grows, and then we update the labels and the distances which start from u of v and goes up to u. So here is one example. So let's say we have these edges or these vertices already there. So this is some intermediate, you can say that some intermediate step in Dijkstra algorithm. So if we are considering this particular edge uz having distance 10, then whenever we have to consider such a new edge, then u is the vertex most recently added to the cloud, and z should not be in the cloud. Then only we can consider adding this vertex to this cloud, and the relaxation of edge e updates distance dz as the minimum of whatever was the initial distance dz that we had. So initially we might have it as a infinity. In this case, initially it was taking me 75 units to reach to z, and now once I consider this edge which goes from u to z, because I can reach to u in 50 units, and then I have this edge E which adds 10, and finally I can reach to Z at 60. So now this edge will not serve much purpose. So the relaxation of edge E, it updates the distance from 75 to 60, and that will be the distance that we are going to consider further in following operations. So here is before starting to all the algorithm, here is one example. So A is our source node, and we then from A we have different possibilities. Okay, so let's say A is the source node. Okay, now from A I can go to B, and that takes me 8 units. I can also go to C, which takes me 2 units, and then I can also go to D, which takes how many units? 4 units. Okay. Then what is the possibility that I will take in this case? I will go with the C2 because that's the minimum possible distance I have. So in the next phase, you can see this arrow, I'm going to add C to my cloud. So my cloud now grows from A to AC, and now in the further computation I'm going to consider all the possible distances from A and C. And now every time the next vertex I'm going to consider should be, or next edge I'm going to consider should have one vertex inside the cloud and one vertex outside the cloud. So when the cloud was only limited to A, I consider these 3 edges, AB, AC, AD. Now among these I picked the minimum distance, which is C. So now my cloud has become AC, and now all my edges will start either from A or from C, and then the endpoints might be B, might be E, might be F, might be D. So what other edges now I can consider? I can still consider AB because it is from A. So I can still consider AB, which is 4. Now AC I have already considered, and now I will not reconsider it because both A and C both are inside the cloud. So I'm not going to consider this edge again. But AD I can consider. So AD I can consider, and now since A and C both are there, I can have another possibility of going to D. So initially AD was 4, but now since I have C also, I can go to D via C. So I can go A, C, D, which is possible in 3 units. Then next thing I can do from C is I can check all the possible edges, and then I can see that from C I have CF edge, which is which takes me 9. From C I have another edge E, which takes me 3 units, and then from C B is there, which takes 7 units. So the only thing that is feasible for me is going from C to D, which is the minimum distance edge, and which will make me reach from A to D in 3 units instead of the 4 units previously. So this edge now will not be of much use to me going directly, because if I go indirectly via C, then that saves me 1 unit. So this is my next edge, or next smallest edge that I can pick, goes from C to D. So now D also becomes part of this cloud, and now in the next iteration I can pick an edge in such a way that it either goes out from A or from C or from D, and it is minimum of all. So from A you can see that pretty much we already covered all the minimum edges. So 8 is not that great. Then this we will not pick because we already know one good way of going to D via C. Then from C, is there any good edge that we can pick? One we already picked, going to D. Another is of 9 units, which takes us to F. Another one is of 3 units, which takes us to E. So initially E was infinite. You can see that I did not have a direct way to reach to E. But now since I know C, I can go to A to C and then C to E, and that's why this is a smallest edge that I can pick in the next iteration, which is CE and having the weight 3. Okay, and when we add this particular path, E becomes reachable in 5 units, because from A to C it takes me 2 units and from C to E it takes me 3 units. So 2 plus 3, E is reachable in 5. So you can also see that initially it was infinite, and D is 4, and after we picked up the best edges, now D is reachable in 3 units and E is reachable in 5 units. So E also becomes part of this cloud. So now we have A, C, D, E, and then we have to consider the edges which are outside this cloud. So either I can consider EB, or I can consider CF, or I can consider DF, or I can consider AB. Now, out of these possible edges, you can see that this is the minimum edge, which is EB. So now the next possible edge that we will pick is CB. And so everything becomes part of the cloud except F. Okay. And now which edge going towards F is the minimum one is 5. And then we pick 5, and then also we change this distance. Going to B was 8 initially, but if we go via E, 5 and 2, then this distance get updated as 7. How about F? Initially F was reachable in 8 units, but so even if we pick this particular route, F is still reachable in 8 units. So we picked this edge, and then every possible edge that we picked up is part of the cloud now. And then the dotted edges are not required for us. So those are relaxed, or those are not needed edges, and so those edges are shown in dotted line, because in any shortest path we are not going to take that edge, because it takes me 8 units from A to B to reach to B, and instead of that I would prefer other edges which will take me 7 units, which is from A to C, C to E, E to B. And so this edge is no longer needed in a path. Similarly, for edge AD is not needed in the path, edge CF is not needed in the path. So this is how the shortest path example works. And in the Dijkstra algorithm, this is a very old solution, like 30-year-old solution, and it was a prime example of greedy algorithm, because at every stage it selects the smallest distance vertex among all the unknown vertices. So you start from any vertex, you find all the edges, and then you pick one with the smallest edge. So if you remember, the very first thing we did was we started from A, we saw all the possible vertices where A is connected by edges, and then we picked the minimum one. And so this is called as a greedy algorithm, where without thinking much we always pick either minimum or maximum depending upon our requirement. So that is called as a greedy algorithm. So this is one example of greedy algorithm. And again, we want to use the Dijkstra algorithm in a given graph. So here in this graph we can see that we are starting from the vertex V3, and then we can go to, so let's start from here. So what is the initial configuration of this graph? So initially v1 is the source node in this case, because I think it should be v3. Okay, so sometimes it might be given to you that you are given a particular source node v1, and then from there you have to traverse to some given node v5. Then in that case you have to find the path between v1 and v5 and so on. So in this case, let's say distance dv0 means v1 is the source node given to us. And then since this is again, we do have some weights that we want to consider in this case. So here are some phases of Dijkstra's algorithm. So initially we have v1 as 0, and then we have v3 to v1 as 4, v1 to v4 as 1. So initially when nothing is known, all other nodes are shown as at distance infinity. You can see only v1 is reachable at distance 0, all other nodes are at infinite distance. Okay, now we can see that from v1, asterisk means v1 is known to us now. Okay, and then we have to find from v1 we can reach to v2, from v1 we can also reach to v4. So I need to update the distances. So instead of now v4 and v2 being infinite, I'm going to change it. So v1 is reachable in 0 distance, and you add 1 to it, then v4 becomes reachable in distance 1. Similarly for v2, v1 is distance 0 and plus 2, so v2 is reachable in distance 2. So these two nodes are known to me. So we are basically growing the cloud in the similar way that we did for the previous example. So now for known node we are going to show it as a asterisk symbol. So now v4, so these two distances are there, v4 at distance 1 and v2 at distance 2. So I'm going to pick the minimum one, and then the minimum one is edge v1 to v4. So v4 is added to my cloud. So v1 and v4 have been shown asterisk on top of it. And now my cloud, now the other edges that I'm going to consider either goes from v1 to outside or to v4 to outside, and I have to choose minimum edges. So from I can see that from v1, v2 is one edge with distance 2, then v4, v6 is another edge, v4, v6, but that distance is 8. So that is we are not going to really consider v4, v7. So v4, v7 is another edge, and it is having distance 4. And so out of this we will select the minimum edge, which is v1, v2. So in the next phase v2 will be added to the cloud of vertices. And now I will consider edges going from v1 to outside, v2 to outside, v4 to outside, and then I'm going to pick the minimum edge. So in this case we can see that from v1 we can go to v4, and then from v4 we can go to v3. So this is we can reach to v3 in unit 3. Then next possible edge is going from v2 to v4, which is 3 units, v2 to v5 10 units. Then from v1 we covered both the edges, so we do not have anything left, and from v2 to v3 2. So out of this 2, 3 and 10, 2 is the lowest one. So our next node that gets added in the cloud is V3. Okay. Now from V3, so here I think I missed one step. We also add from V4, we can have either I can have V go to V3, which will be 2, or I can go to V5, which is also 2. So either ways we can select any one of those. So one we selected now and one we select later on, because this is going to be, again, if we consider ages going from V5, then this age is of weight 6. So the cloud is growing, and again in the next time also age going outwards from V4 is the minimum age. So we are going to consider V3 as part of the cloud. And then again we will consider all the ages going from the cloud to and outside the cloud. So this is one age 5, this is one age 8, this is one age 4, and this is one age 6. So this is the minimum age 4. So the next vertex which gets added is V7. And in the next phase, we are going to consider again from cloud to outside cloud, and that those are only these ages 5, 8 and 1. So here we picked the minimum 1 age, and then we also made V6 as part of the cloud. So here we are just making sure which ages we want to traverse, and the other ages we can show as the dotted lines. So here is one running example, and this can also be shown as how so the same thing is shown here, a diagram, phase by phases, that initially we had one V1 0, then after that we could reach to V2 and V4. So we picked the minimum 1, and after V4 is declared known, the distances of all the vertices we can reach from either V1 or V4, and then we are again going to pick up the minimum age and so on, and when then that will be V2 and then so on. So what we just discussed, looking at the graph, the same thing they have shown here. So this is the running of this algorithm. So we started from vertex A. Now consider all the outgoing edges from A. We have AB with 2, edge AC with 1, edge AD with distance 4. So initially only A is known to us. So what will be the next vertex that we want to select will be the minimum age. So from A, minimum age goes to C. So C should be the next known vertex, and here we can see C is the next vertex, and now we have the cost associated with reaching to C, which is 1, cost associated with reaching to A, which is 0. For rest costs we are not yet sure. From A we can reach to B, though we can also reach to D, and so these are the possible costs, and if we get something less than that, then we are going to update those costs. Okay, so order of known vertices, first A then C. Okay, what is the next possible ages? So if you see from C we have one age with 11, and from A we had these 2 ages which are remaining, and then we picked the smallest one, which is 2. So my cloud now has A, C, B. Okay, so what will be the next age? So from A I have AD, which is 4. So this is possible age. From B I have BF. This is one possible age. I can consider 5, 10, but those are greater than this, so I will not consider. So these are 2 possibilities which I also have these possibilities which I can consider, and then I consider the one with the lowest out of this. If I have path from B, I can reach to F in 4, or from A I can also reach to D in 4. So let's say I picked D, and then the next, what will be the next node that I can add will be again F, and then what is the next possible edge or minimum edge that I can add will be 3, because there is all these other edges are 5, 10 and 7. E is not yet part of the cloud. 5, 10, so the minimum edge is 3, so we added 3, and then H is also part of this. So the next minimum edge is HG, so G is added to the cloud, and the distances are updated. You can see now we can reach to B in 2 units, then we can reach to F in 4 units, we can reach to H in 7 units. So we keep on adding or keep on modifying the distances depending upon what path we are choosing. And finally E is the only node that we need to cover now, and we covered it from G to E, that is the minimum path directly going from. So here we can see that this is the path and these are the updated costs from